Everyone. I welcome you all for a presentation on the applications of polar coordinate system, a topic belonging to the subject mathematics for CSE stream. Let me introduce you to myself. I am Bharath M, belonging to Audi section, second semester, Sri Venkateswara College of Engineering, Department of Computer Science Engineering and Artificial Intelligence. The subject I'm going to explain through this presentation, through this video, is mathematics for CSE stream, and the topic I've chosen is about the applications of polar coordinate systems. Let me introduce you to myself, and the same way I'll introduce you to the presentation. Welcome to the presentation on the applications of spherical polar coordinates in vector calculus. Today, we'll explore how this coordinate system simplifies integral calculations and its significance in various mathematical contexts. Moving on to the next slide, basics of spherical polar coordinates. Spherical polar coordinates comprise three main components: the radial distance denoted by r, azimuthal angle which is denoted by theta, and polar angle denoted by phi. Together, these define points uniquely in space, forming the foundation for simplifying vector calculus operations. Line integrals in spherical polar coordinates. Line integrals quantify work and circulation. Using spherical polar coordinates, we express line integral as a dot product involving the unit tangent vector and an infinitesimal displacement. This approach elegantly captures orientation and magnitude. Moving to the next slide, calculating line integrals, an example. Let's dive into an example. Consider a curve defined in spherical polar coordinates. We'll walk through the steps of calculating a line integral, showcasing how the choice of angle limits align with the coordinate system's symmetry. Let us now move on to the next slide of the presentation. Surface integrals in spherical polar coordinates. Surface integral measure flux across surfaces. In spherical polar coordinates, we formulate surface integral using the unit normal vector and infinitesimal area element. This framework efficiently captures flow through surfaces. In the next slide, let us look on calculating surface integrals. To illustrate, we'll work through a surface integral calculation using spherical polar coordinates. The inherent symmetry of the system simplifies the expression, making intricate surface problems more approachable. This is where the polar coordinate systems are applied in real life. Now let us look at some theorems and postulates. One is the important one of polar coordinate system, that is Green's theorem, as with respect to the spherical polar coordinates. The Green's theorem connects line and surface integral. Using divergence and curl, we express this theorem. In the context of spherical polar coordinates, it bridges integral types, highlighting the coordinate system's adaptability. Moving on to the next slide, that is the Stokes theorem in spherical polar coordinates. Stokes' theorem links line integrals around closed curves to surface integrals over enclosed regions. With spherical polar coordinates, we apply this theorem, showcasing its versatility in handling rotational symmetries. This theorem is practically applied only during rotational symmetries. Let us go to the next slide of the presentation. that is the Gauss theorem in spherical polar coordinate. Gauss theorem or the divergence theorem ties volume integrals to surface integral. When applied in spherical polar coordinates, it takes advantage of radial symmetry, simplifying calculations for a variety of problems. Moving on to the next slide, what are the advantages and challenges of spherical polar coordinate system? Spherical polar coordinates offer clear benefits, simplifying calculations in symmetric scenarios. However, challenges arise when dealing with non-spherical cases. Understanding these nuances empowers effective problem solving. What is its applications in mathematics? The application of spherical polar coordinates span mathematics, from solving complex equations to modeling physical phenomena. These coordinates find utility in diverse mathematical fields, showcasing their versatility. Comparison with other coordinate system, comparing spherical polar coordinates to Cartesian and cylindrical system reveals their unique strength. For radial problems, spherical polar coordinates shine, streamlining calculations through their natural symmetry. Moving to the next slide, what are the practical implications of spherical polar coordinate system? Beyond theory, understanding these applications has tangible real-world implications. From physics to engineering, the use of spherical polar coordinates aid in solving problems with precision and efficiency. Let me conclude the presentation to wrap up. So, spherical polar coordinates significantly impact vector calculus and mathematics. Their ability to simplify complex calculations and address a range of scenarios underscores their importance. I thank you all for being a part of this video. Let's meet soon in the next video. Thank you.